Hello, in this video I'm going to say a little bit about lasers just to give a basic idea of what it is that they're achieving and how they work. I mean, I'm not going to go into loads of details because they're fairly complicated, but we are in a section on optics, so it's useful to know a little bit about lasers. It's something that people ask about quite a lot. So first of all, where does the name come from? So I've written it out as a normal word, but really the laser bit, I mean, this is an acronym. We've got these 5 letters here standing for light amplification by stimulated emission of radiation. So that's already giving us some clues as to what's going on. We're wanting to do light amplification, and we're wanting to do whatever this thing, stimulated emission of radiation, actually is. So, and really we're trying to organize our energy here. If you think of places where we might be getting photons from and how photons get emitted by things, there's 2 things that we've encountered commonly so far. We've looked at thermal radiation. So in our thermodynamics section, so this is where you've got charged particles jiggling around. So charged particles with some random motion, so they've got random accelerations going on, and you're going to get then photons emitted because you've got these accelerating charged particles. But these photons are emitted at random in random directions and have a distribution about some particular frequency based on what the temperature is. So the temperature will determine the peak frequency that we're getting from this thermal radiation, and we're going to get a distribution around this. So the thing is then with thermal radiation is we've got a lot of randomness in it, and we've got a spread of what the frequencies are going to be. So okay, they're spread about a particular value, but still. So that's what's going on with the thermal radiation. But then we've also got stuff with the excitation of electrons. So if we've got our atom, we've got our nucleus with various energy levels that our electrons can exist in, and these are fixed. So if you've got an electron in a higher energy level and then it de-excites down to the ground state, it's going to release a photon of a fixed, it's a determined frequency. A certain amount of energy is going to be released here as a photon. So this is much more organized in terms of what gets released. We've got photons that are all much the same, which is what we want if we want to get organized, coherent light. When we've spoken a lot about coherent waves, if you want some coherent light, we need stuff which is going to be at the same frequency. Well, this is giving us a way to do it, but we've still got a problem of it being random to a certain extent if we don't do something in order to make it more organized. Because these electrons, I mean, they can de-excite. We don't have that much control over them generally, but we want to be able to control when these things are emitted. But if we can then do, this is where the SER laser is coming in, this stimulated emission of radiation. If we can get some control over when these photons are being emitted, then we can get loads of photons at the same time of the same frequency all being emitted, and then we can direct those, and we've got ourselves a laser. So how's this happening then? So you get some material that's going to be inside the laser. I mean, sometimes you'll get helium neon lasers, so you've got some gas there. You get carbon dioxide lasers. I think it's the gas ones that get used in a lot of industrial cutting and welding and things like that. You get chemical ones. You get some solid state ones where you'll get a crystal which has been doped with certain ions, a bit similarly to how we'll be talking about semiconductors when we get on to the section on electricity. So you've got some kind of material, and if this is then pumped, it gets pumped with energy. So you've got to put energy in order to get the energy out. We're not just magicking up energy from somewhere. You pump this energy in, so it might be pulsing light at it, or pulsing electricity at it. You're doing something in order to get a large percentage of the stuff in the laser, of this material, up into a certain excited state. So you're pumping up loads of these atoms, so that they're in this excited state. And the material is chosen not only that you can get the atoms excited, but also that they'll stay excited for a relatively long time. You don't want it that as soon as you're pumping all these electrons up to excited state, they just decay, de-excite straight away. You want them to hang around a bit to give the opportunity to then de-excite them through this stimulated emission. So that's how they're picking the particular materials that these lasers are made from. So you pump it all up, and once you've got a certain amount, there's more excited atoms than not. You get this thing called population inversion, which is more or less saying we're good to go now on the laser. And you get then this stimulated emission that goes on. So they set up these mirrors. They're like half mirrors. So it will let half of the radiation out and keep half of the radiation in, say. You get these photons appearing of a particular frequency, and half of them are now bouncing up and down inside the material. But every time one of these photons goes past one of these excited atoms, it stimulates the emission of another photon of the same type. So you're getting this cascade of de-excitation. One of them goes, creates the photon, that then goes past another atom, which is in the excited state, stimulates the emission of another photon. We've now got two of them. These are now cascading through the material. Half of it's now bouncing backwards and forwards all the time, it's like a chain reaction of photon emission, all at the same frequency. But you've also got half of it getting emitted into the laser beam. So we're doing two things here in terms of the coherence. You're getting high spatial and temporal coherence. In the coherence video, we spoke about these two ways that you can describe coherence. We've got the temporal, as in the time coherence of the emitted photons, because we've all got the same frequency on these things. So frequency is the same. It's all coming out. And with these lasers, I mean, they can, if you've got a beam, even say, maybe 300 meters away, you've still got the waves more or less in step. They're in phase with each other, even over these long distances. So we've got this temporal coherence of the beam, and we can also get spatial coherence of the beam as well, in that it's very strongly directed. We can have these beams. I mean, you've seen laser beams. These wave fronts are very strongly collimated in one direction. So we'll be able to get both forms of coherence here in this laser beam. So yeah, this is what's going on. It's just controlling the energy. You're still having to put energy in. We're organizing it in terms of the excitation of these atoms, and then we're stimulating the emission so we can then organize the energy that's being released into this coherent beam. So yeah, it's just a great way of organizing energy. And we can see how much lasers get used. Okay, I've already mentioned cutting and welding and things like that, but you've got them in DVD players, barcode readers, laser eye surgery, range measurement, things like this. So yeah, there's loads and loads of uses of these things. I mean, in terms of the history of this, I mean, I think lasers, they started getting used in maybe the 1960s onwards. Before then, you had a thing called masers. So light lasers, but with an M at the start. And these were microwave lasers, essentially. So we've now people, when they talk about masers, we're talking about electromagnetic waves that are in the microwave to radio, say. And if you've got stuff which is in the light going to gamma wave direction, the gamma rays at the shorter wavelengths, the higher frequencies, then these will be our lasers. These will be our masers going on there if you've got longer wavelengths. But it's a similar sort of process. But the lasers started coming in the 1960s. The theoretical foundation of lasers, I mean, Einstein was talking about this back in the early part of the 20th century, the 1910s and such like. Einstein was getting these theoretical foundations put together, but it took a while for people to actually be able to construct them at a working level. But yeah, now they get used all over the place. They're pretty commonplace, aren't they? And you pick your materials depending on what it is you're trying to achieve, whether you're trying to do some heavy duty industrial cutting and welding, in which case you've got something like a helium neon laser or something like that, or whether you want some kind of solid state semiconductor type setup, which you might have in a laser pointer or something like that, where you don't need as much energy kicking around. So yeah, there you go. It's just a quick overview, just so you've got a basic understanding of what's going on with lasers. Can't really get into it too much depth, but hopefully that gives you the idea.